So my name is Steven Huang. Our relationship between Alice and myself started as a pilot program within the INCOSE organization to mentor a mentee. And so while I had been a system engineer for many years, Alice was new to the industry. And we wanted to better understand how she wanted to use system engineering principles for her work in her industry. Which happens to be in, as was described, right, more of water treatment and waste management. And so we started to explore the different areas of pain points that she had seen in her industry and how to apply system engineering methods to that. So, with my background more in aerospace and defense, we had a common understanding of system engineering processes, but how to apply it to problem sets unique to her industry was part of the interest and exploration together. As myself, I'm going to let Alice introduce herself.
Hello, I hope you can hear me. I'm Alice Cellamare from p2m Berlin. Yes, as Martin has mentioned, we work in the water and wastewater sector, and I was lucky enough to be able to take part into the INCOSE Mentoring Program, where I met Steven as my mentor, and we developed this method together. Back to you.
Thank you. So yeah, actually, Alice is being very humble. She is very, professional and interested in learning about system engineering and learning tools. So it was a very interesting and collaborative relationship. We started out looking at different problem areas first that we were encountering, and then, how to approach that. So in today's outline, we're going to look through different safety assessment methods that are used in the industry. As well as some known tools that exist for Capella, and where we thought maybe there was some gaps in how to use safety assessment in a more robust way. And so that embarked upon our project, where we are then going to define the scope and the workflow for how we came about doing safety assessment analysis for this particular presentation, and the methods that we were looking to develop and mature as part of this holistic search for failure modes and effects prior to the completion of the design phase, and doing so in a more automated way. So we'll walk through a very specific example that Alice has been working specific to her industry, and then close with some conclusions. There will be a number of polls throughout this presentation, and on the slides where you see this blue star, that means a poll is coming. And so towards that end, the first question or poll that we would like to ask is what industry each of you are representing. So as myself, I mentioned I was in aerospace and defense, but there are a lot of other folks on the line from a disparate, variety of industries. And so please go ahead and fill that poll out, and then we can review that once the responses are in.
Ooh, wow, I already see 5 people from aerospace like you. It's interesting.
Yeah, we were hoping for a distribution of people from different industries. So it's nice to see from everyone that's online today how we are represented across those. And we recognize we may not be able to, uniquely identify all of them, but it is good to know that we have a cross-section of those industries represented today.
Nice, at least one from infrastructure.
Was that right. You, Alice?
No. Okay.
Okay, so on our next slide, we're going to talk a little bit more specifically about the safety assessment methods that we looked at. So the 4 that were on the top of our list that we wanted to explore were fault hazard analysis, fault tree analysis, systems theoretic process analysis, and failure mode and effects analysis. So the first 2 methods were very interesting to us because they identified specific functions and or their relationships within the modeling elements that we were looking at, but they didn't go far enough in terms of understanding components or processes that we were looking to identify in an automated way. So then we looked at more closely at STPA and FMEA and found that there's actually an interesting combination and synergistic relationship between STPA and FMEA approaches to finding safety assessments or hazards. And so we wanted to look more deeply at those as to why those combine to provide a more robust insight into hazard analysis. So the next slide, before the next slide, I'm sorry, we do have another poll, which is specifically which of these methods you might use it or see in your industry. So thank you again for your feedback. I think that there's going to be a number of different responses similar to the number of different industries we represent. And so some methods, take, root in some industries over others. And so we wanted to make sure we understood what that cross-section was and how they impacted each other. But it looks like most of the responses are involved with FMEA, similar to myself, although that FTA is also used very commonly.
It's interesting that some other are also there, and some STPA users also. That's great. That makes the input even more interesting. All right.
Thank you, everyone. So on the next slide, we're going to go a little bit more into why we chose these particular methods. And the article by Cellamare, who did a case study looking at FMEA and STPA in particular, and why they identified both common and distinct hazards among those two methods. And so the interesting thing to note is that STPA tended to find more things like component or software interactions better than FMEA, but FMEA identified more system and component hazards than STPA. So the overlap or combination of those proved to be very robust in the identification of hazards, which is why we happen to choose the combination of these approaches in our algorithmic approach of doing a search within a Capella model with both of these constructs. So on the next slide, we wanted to identify some known tools that already exist in the industry, and they do provide a number of good insights, unique to their own implementations. So Safety Architect has implemented methods for FHA, FTA, and FMEA, and similarly, Attica for Capella has also done the same, but they focus slightly differently on the Arcadia diagrams. So Safety Architect looked more at the system architecture, and then more at the physical architecture for FTA and FMEA, whereas Attica for Capella looked at FTA more at the logical architecture, and then FMEA used the physical architecture. And the interesting thing here that we wanted to note is these particular approaches appear to require a user to identify the components that would need to be analyzed for failures, whereas we were looking for an approach that actually did that search and discovery independent of what the user thought. So it does require the model to be a little bit more mature, but our algorithmic approach, it provides a more holistic search of potential components or processes or functions that fail than one that would be identified by a user, whether they be knowledgeable or not, right? So the idea was to help facilitate the identification of failures in a more automated way beyond what these tools were able to do under themselves. So there was a little bit of a gap for what these tools were able to do, in terms of analysis versus the identification of that failure. And so on this one, there's a poll that actually identifies which of these tools, if you use them, do you use currently today?
All right.
So thank you again for participating in these polls. This is very valuable feedback for us.
Thanks. It's great to see how so many responses. Oh, we have a couple users for each tool, and also other. All right.
Ooh, a lot of other.
Yeah, that's very interesting. At p2m, we've only experimented with these two, but would be very interesting to know what hides under this category. But yeah, that would make the time explode. So I guess we'll move on. Thanks a lot.
Yep, thank you. So here we're going to share, presentation of this slide. Obviously, the project scope was really focused on the identification of failures as opposed to evaluation. And so this is not intended to aim at, substituting any safety analysis method, but rather provide a modeler with a model-generated failure list from the very beginning. So naturally, it is occurred towards the end of the design phase, but well before development.
Oh, right. Does that pause me and I should continue? Okay. Thanks, Stephen. Yes, exactly. So we're not looking to substitute any tools, workflows, but we're looking at adding a step before the use of these methods that have been developed, which would help us understand, like would help us squeeze the model for all the information that it can itself provide in terms of which failures are possible or which failures are even imaginable, starting from the model architecture. Meaning we are going for a quantitative approach. We are looking at just listing all the possible failures that can be identified by simply looking at the model, and not having any qualitative evaluation at this first step. Also, we don't consider failure causes at all during this phase, because this would decrease the amount of failures we would find. There might be some failures that, for example, identify a valve that doesn't work anymore. Is it clogged? Is it rusty? That doesn't matter. It's we only realize that, okay, this component is not available at this point, and that's all we want to do in this first phase. Also, we wanted to point out that our efforts are limited to the physical architecture layer of the Arcadia framework, and this is because on one side, because it is the most complete layer in terms of components, where we should have practically all the components our system is made up of, and also because it's comprehensive in terms of model elements. We have the behavioral components as well as the node PCs, which makes it advantageous for the development and maybe for a future application also on other layers. There, I would like to ask you a first opinion question. Meaning, we have laid out a little bit of what our goals are, and at this point, we would like to know if you think, just with this information, what do you think? Is it an approach that you can imagine working? And for this one, we have left you room for a short answer, and we're going to read these answers at a later time in order to compare them then to the ones you will give at the end of the presentation. So I would like to leave you a couple seconds to answer, and but we will leave the poll open for the next couple of minutes in case someone wants to continue writing after we have moved to the next slide.
And we recognize that it might be difficult to ascertain, right, if this will be successful without an example. So we do have one later. But just from an overview perspective, it would be helpful to get your understanding of, does this approach look feasible? Does it look like it would reveal some interesting, results or analysis? And have you seen anything else like it that might be, another compelling a way to identify failures or safety hazards?
Yes, this might also be the right time to point out that we have seen that the last talk of the next session number 4 tomorrow, will cover a topic which appears very similar to ours from the abstract that we have read. So in addition to our example that we will present later, it might be very interesting to follow up on what the colleagues of the last talking session 4 will tell us. We will certainly attend that. I don't know if they're in the audience right now. That would be great to know. But I don't know if we can.
At least we'll advertise for them.
Yes. Okay. So as I mentioned, we'll leave the poll open for another little bit. But meanwhile, let's move on to the next topic, which is which model elements are relevant to this analysis. We focus on functional aspects, meaning functional exchanges, functional chains, and especially exchange scenarios will be crucial to this analysis than modes and states, together with their triggers and then entry, do, and exit functions. And also we include situations and configurations, especially situations. These are not native objects of the Arcadia framework. They are brought into the Capella environment by the VPMS add-on, the modes and states viewpoint that was developed by Thales in the last years. And that is why we have a short introduction to it, just in case someone is not very familiar with it. These two objects are called configuration situation. Here you can see a schematic representation of a physical architecture layer. A configuration is a subset of the system elements, meaning that we have excluded a couple of them from the system, and only the rest are available to us, while a situation is a collection of component states, meaning for each component we can have the indication on in which state the component is in the situation we are taking into account. For the purpose of our project, we have adopted a strategy which consists into assigning states, also the information of whether a component is available or not available. Meaning, like, for example, if states 1 and 3 in this schematic representation were set to unavailable, then this would be equivalent to the configuration we see in the on the left hand side. Yes. So what did we do exactly during this project? We took our time to determine, are all failures the same, or are there different types? Depending on which type of failure we are dealing with, how do we identify it? How do we assess its consequences simply based on the model architecture? How do we render the conclusions that we draw from this analysis to a human user of our tool, and then to allow them to evaluate the failures? And then we coded the procedure in PyCapella in Python, using the PyCapella MBSE library instead of Python4Capella, although we also tried with Python4Capella. They are very similar. And then the next step would be to test the result on a company model, which we have not completed this phase, but we will still present you with a short example of what that would look like. So the failure types we have identified are three. Component failure happens when a component is not available, simply like a physical component or also a function. That's considered a component failure, and it would be represented on a physical architecture blank diagram. The second type would be a function or process failure, which would happen when a function or a state or mode is realized at an unwanted time or is not realized when it should. And this would be represented on an exchange scenario or a physical function description scenario diagram. The third one is a content failure, and this would mean an attribute is set to an unexpected value. Either it's a component attribute or an exchange item attribute, and this would give rise to certain states or modes that we would see in a state machine diagram or an exchange scenario. It's a bit abstract to this point, but I would still like to know from you if you think these categories are exhaustive or are right. And yes, while I close the last poll, and yes, it would be very interesting to know, okay, just by hearing them once, what you think about these categories. Since we are running out of time, I will continue meanwhile, and whoever wants to skip this poll is also welcome to. Right. So our method consists in we have identified three classes of failure. We will focus on component failures for our example and our explanation. component failure is analyzed as follows. We define which component is failing, and then we assess whether other components are affected by its failure. For example, when a Node PC is failing and there are behavioral components deployed onto it, they will fail with it. So we will have a list of affected elements in the end. The next step would be to assess the impact of these failure onto each exchange scenario that contains the components we were talking about. The result of this analysis will be expressed as a situation change, meaning that we will have an exchange scenario we run through, and at the point where the failure occurs, we will assess what happens in terms of a new situation. This will become apparent if we look at the example. In this slide, you can see the sequence of the affecting mechanisms through between the elements. For example, Node PC can affect the behavior PC, which can affect the component exchange, which can affect the functional exchange, which is assigned to it, and so on until we reach the exchange scenario level and the capability level. The scenario analysis works as follows. We take an exchange scenario and we break it down into steps. Each of these steps corresponds to a situation which is planned. And then by identifying one of the steps at each time, we will understand, okay, what will happen if the failure that we are analyzing at this moment appears during this step of the scenario. And then we will move to the next step and to the next step and to the next step. And so our algorithm will go through each scenario and communicate with us in order for us to understand, is a failure as important at each moment, or will it be, for example, more critical if it happens later or earlier? Right. I propose we skip the next poll. I will just move on since it's just about an impression and I think we're really late. And there you go. Let's dive into our example. The model we used is a sludge drying plant. We produced this model for one of our customers. And for this component failure analysis, we consider the component named NAB_0AA400, which is a valve. And as you see, it is grayed out in our physical architecture blank, in which you can also see all the functional chains that we consider during the nominal operation of this system. The next step will be to identify, okay, when this valve is failing, what other components are affected by this failure. In this case, it's a very short list. We have the valve. This area is just a zoom in of the diagram you were seeing before, and two functions, the two functions that are allocated to the component we are seeing fail, and the two functional exchanges that start from those functions. What does this system, the functional chain, which is represented in the green color, covers the subsystem, which is comprised by a tank, which hosts a pump and has a first flush system. This one is the valve that is failing in our example. The system works as follows. When the water level is higher than 90%, this valve opens and lets the first layer of the fluid, which is the dirtiest, flow out. And when the level reaches under 90%, then the pump will control the level through a PID level regulator. So yes, so this green one is the functional chain that we are analyzing, since it's the one that's affected by the component failure we are taking into account. This is the functional chain we are talking about. I apologize because the model is in German. It just means level regulation. And the functional chain of the level regulation corresponds to the exchange scenario that we have here. So as you have seen in the explanation, we have here all the components that are involved in this functional, in this exchange scenario. And this rectangle you can see here is an alternative operand, and it describes the control action of activating the first flush when 90% is reached. When we divide the exchange scenario into steps, we are able to produce an overview of each state machine, um, which is allocated to each component, and the states they have in each during each step. For example, before this function is run, this state machines have the states available, active, available, not defined, available, and not defined. Whenever you see a question mark, this means that the exchange scenario does not tell us which state the component is in up to a certain point. For example, here we have a state fragment that means not running, and it means at this point the pump will stop running, whether it was running or not before. Let us assume that our failure appears during step 1.6. And so what will happen is that our valve, which is this component here, will not be available. It will not be able to open as it was shown before. It was supposed to open in step 1.7, but it will not. So the last two steps, in the last two steps, the valve will be not available, and the state is not defined. It will stay in the state that it had before. This means we can have two failure situations. If the valve was closed before the failure, then it will be not available and closed for the last two steps. If this valve was open, it will be not available and open. And this is all steps that the algorithm goes through in order to identify these situations that you can see in these two tables. Thankfully, the library we use is able to deal with the modes and states viewpoint, so it can generate failure 1 and failure 2 as situations, meaning that you will be able to see in the situations table failure 1 and failure 2 with all their states related to the components that we are dealing with. This one you see here is the valve we are considering, and it is not available in both failures, but in one it's closed and in one it's open. When we look at the structure diagram, we can see that both components that are affected by, not affected, that are, let's say, not allowing any flow in this configuration are the pump and the valve, which are the only two ways out for the fluid from the tank, which means that this situation is not desirable. It will probably lead to an overflow of the tank. This is the way that a person that's using this tool would be able to visualize and assess the effect of this failure in a way that's not very what's the word, that's not that's not very left to someone's imagination, but it's based on diagrams and hard facts, so to say. Meaning that once a person is presented with this overview, they will be able to make a more informed scoring and evaluation of the failures. This is what the output after the scoring would look like. For our component failure, we have failure 1 and failure 2, and we can imagine that a person would score the danger, let's call it, from failure 1 as a 5, since it will lead to overflow of the tank, and failure 2 with a 0, because it would not lead to the overflow, being the valve open. And then we have several other failures that we worked on in our example. For example, another one might have a 10, because the consequences are more dire. Yes, so after the situations are scored one by one, you can see, as you can see here, a single failure will give rise to more than one situation. We can summarize all this information in a failure overview table. For example, this would be the tab in our file that considers all the component failures, and when we reach the line that represents the failure of our valve, we can say that the scoring is in total a 5 as far as situations are concerned. And then we have other information about affected components, affected functions, scenarios, and capabilities. And then we have other fields that are typical of FMEA, and these will have to be filled based on the information that we collected, maybe hopefully using one of the tools that we already know, and thus completing the cycle of the failure evaluation. At this point, I hope that the example was clear, and I would like to ask you for your opinion one last time, but twice, meaning that would like to know what your if you can see this working again, and then also if you would like to formulate a personal feedback, I will open one more poll for it in a minute. Interestingly, most of the people are hitting I would need more info to decide, which I am interested in, which is actually a great result. And no one is sure that this will not work, which is also nice. And yes, so yes, I'm aware that we did not go into very much detail about as far as the example is concerned, also out of time concerns. But of course, we will put our contacts in the last slide. So if anyone is interested in having a closer conversation about this, or maybe cooperating in some way, would be very happy about it, and we invite you to contact us if you're willing to. Well, Martin, if you think it's a good idea, we can also start answering the questions while people formulate the feedback, because that would give them more time and more ease. And
Yeah,
yes.
I think that's a good idea. Okay, let's go. The first question, the most upvoted. Can this tool also detect multi-functional chain failures? And if so, how does the library rate those?
Multifunctional chains would mean which affect more than one functional chain, or this is a bit
I assume so.
yes, I mean,
That's how I understand. But Vinayak, maybe if we are mistaken, maybe you can tell us in the chat.
yes, please. If you are referring to failures that affect more than one functional change, then of course, because each and the algorithm identifies all the functional chains that are affected by each failure, and it can also extend the analysis to functional chains that are not directly containing the component we are talking about. Also, we have to point out that our example was only focusing on component failures. There is also a type of failure that concerns functional chains directly. The functional or process failures, those are failures that look directly at the function fragment in the exchange scenarios. So yes, that's just on the side. But of course, yes, the algorithm will detect all functional chains that are affected by each failure, and then analyze each functional chain / exchange scenario separately. So if you mean if there is any interaction between the functional chains, then this is only considered if the exchange scenario contains a reference operand to the other exchange scenario. I don't know if that's clear enough. Like you have the same as when you as when you introduce a loop or an alternative operand, you can introduce a reference from one exchange scenario to another, and that's how the algorithm connects the exchange scenarios to each other during the same scenario breakdown, or else the analysis will be separate.
As your failure identification process is based on the physical layer, how do you cover software failures? Have you considered to use logical or functional layers for this matter?
Our control systems are modeled in the physical architecture layer. I mean, we are very much not sure if our way of modeling is very um, is very standard or very appropriate, honestly, because we are kind of a self-taught and systems engineering enterprise. So but like we base our judgment on the exchange with other users. And but as you have seen in the, maybe I can show it also in the in one of the slides. Yes, this part of our model called PLS. This is the control system, and especially this behavioral component that was involved in our functional chain is the control loop, the control cycle that we program into the control system. So software failures in this case are also covered in the physical architecture layer. This might be a very nice input if you think that this is not an appropriate way of doing things. Then we would have to look into it. But for now, it's covered like that. Our software is together with the hardware in the same model layer.
This one by Andy. Interesting presentation. Have you managed to validate the model analysis with a real system or component? Did you generate any test documents to help with the analysis?
No, we did not validate the analysis yet completely. We have started the validation, but we are not that far yet that we can say we have validated the method. That is also why we are asking so many questions during the presentation, because we would like to gather as much feedback as possible from others before we finish the implementation and we put in the last we enter the last phases. Yes, actually we were planning to do it, but we are not that far yet. As far as test documents, I'm not sure I understand exactly what that means. Steven, do you have a...
Yeah, so sometimes, models are able to also generate test documentation about what was evaluated and what the results were. So we have not taken that next step in terms of, producing those documents, but I do think that would be valuable and possible given the analytic results we've seen to date. So thanks very much for the idea.
Thank you. Yes, and also I'm hoping that tomorrow's presentation will also enlighten us a little bit about that, because it seems like they have done this step.
This question, how do you expect it to scale regarding algorithmic complexity and execution time when applied on larger models, and maybe some other aspect that might have been forgotten?
Yeah, I honestly, I do not think that this algorithm will reach any huge running time, even if applied to larger models, because the analysis is really simple. So I yeah, personally, I cannot see that happening in our industry, but maybe yeah, if this was applied to um, is if this got more complicated and was applied to very large models, I would not have an answer for you, to be completely honest. It's like now we are running the script on Visual Studio through a Jupyter notebook. So it's like it's really simple. It just goes step by step and produces the output and writes it into the Excel table, um, and also produces these situations we were talking about. But that's it. Like it's a very that is also why we were a bit in doubt in the beginning to whether this is this makes sense at all, because it seems very intuitive that having an MBSE model of a system should tell us more about failures, about possible failures, than what um, than what we receive by just looking at the diagrams. You know what I mean? Like when we use tools as like such as Safety Architect and Attica, then we have to select which components are failing and how, and what is the severity of this failure, and so on and so on and so forth. And the point of our work was exactly to say, okay, but we have exchange scenarios. We know when functions are used, and we have situations which are a nice way of enriching the Arcadia framework, I think. So why don't we use these elements to ask the model which failures are going to happen? Like it should know a little bit, at least. That's that was the base of what we tried to do, and in the end it turns actually out that it is fairly simple as an analysis. um Other aspects I also wouldn't know. So yes, I mean, it might be that during our test phase we will get back to you and tell you, actually, you know what, you were right. But for now, I I don't know.
Okay, nice. Thank you for the answer. And that was the last question we have here, and we're it's about the time to conclude. So I think
Yes.
we can finish now. But in any case, thank you very much for presenting us that work. It was really interesting. I really liked what you make with some scripting around the Capella models. It's interesting to see that. Um, so yeah,
Thanks
thank
a
you
lot.
again, and I hope you got the feedbacks you wanted and that
Yes.
it will help you.
Yes, maybe just as a last thing, I would like
Mhm.
to display our contacts on the screen so that people can contact us if they want, although I guess that they will be somewhere. And of course, we will read carefully your input. I hope that it is saved somewhere. Um,
It should be. I'm not very familiar, but I think it should be.
okay. Then I'm going to copy paste the last answer just in case. Okay, well, I would like to thank everyone who participated and for their feedback, and also I would like to thank Stephen for helping in this in this project, and you as organizers.
Yeah, we're very thankful and appreciative of all the tailoring, like the similar presentation, right? The tailoring of processes and methods using a model-driven approach, we think really is going to be a difference maker by reducing the potential for human error, right? So thank you very much for your feedback. Thanks to Alice for all her hard work in putting the presentation together. We really thank the audience and their feedback on all the different questions, and we will keep you informed on our status as we proceed to test this algorithmic approach in a future form.